viewers, welcome to CEC-UGC online lectures. In today's lecture, we shall be discussing substitution reactions of alkyl halides. It is not only that alkyl halides undergo nucleophilic substitution reactions. There are some other classes of organic compounds such as alcohols, ethers and amines which also undergo nucleophilic substitution reactions. So, we shall be discussing these reactions in a series of lectures where we shall be covering the fundamental concepts of nucleophilic substitution reactions along with their mechanisms. As you know, alkyl halides are polar in nature, as the bond between the sp3 hybridized carbon and the halogen atom attached to it is polar in nature. The halogen atom is more electronegative as compared to carbon, hence it pulls the electrons towards itself through -I effect, as a result of which carbon has a partial positive charge and is electrophilic in nature, whereas halogen has a negative charge. As alkyl halides are polar, that means the CX bond is highly polar and undergoes heterolytic cleavage easily. The halogen atom can leave with its bonding pair of electrons to form a stable halide anion. This property makes alkyl halides one of the most reactive families of aliphatic compounds. Alkyl halides can undergo substitution as well as elimination reactions. In a substitution reaction, the electronegative atom or group of atoms is replaced by another atom or a group. In an elimination reaction, the electronegative atom or group is eliminated along with a proton from the adjacent carbon, that is the beta carbon, resulting in the formation of alkene. On your screens, now you can see the substitution reactions versus elimination reactions. The atom of the group that is substituted or eliminated in these reactions, that is substitution or an elimination reactions, is called a leaving group. As you can see, when we carry out a reaction between an alkyl halide and a nucleophile, this nucleophile can substitute an halide anion, resulting in the formation of a substituted product. Whereas, if this nucleophile helps to bring about elimination, that is removal of halogen from alpha carbon and proton from beta carbon, then it results in the formation of an alkene. In this process, a new pi bond is formed between the two carbon atoms. Substitution and elimination reactions often compete with each other. It is the structure of the substrate and the strength of the nucleophile which are the decisive factors to find out whether elimination reactions will predominate or substitution reaction will be accompanied by an elimination reaction. Alkyl halides are versatile compounds which can give diverse reactions. Substitution reactions are important reactions of alkyl halides because they make it possible to convert readily available alkyl halides into a wide variety of organic compounds. That is, Since the halide anion is a good leaving group, we can easily convert alkyl halides into cyanides, alcohols, isonitriles, nitro groups, and we can thus use organic halides to bring about organic synthesis of different functional compounds containing different functional groups. On your screens, again you can see the general reaction for substitution of an alkyl halide. In this, a nucleophile reacts with the electrophilic carbon of an alkyl halide, resulting in the formation of a product and a leaving group, which is an halide anion. Since nucleophile is replacing the halide anion, these reactions are known as nucleophilic substitution reactions. So before we proceed further, let us familiarize ourselves with the terms which have been used in the above general reactions. What is a substrate? A substrate is a compound which gets attacked and is modified by a given reagent into products. It is the concentration of the substrate which changes during the course of reaction. Here, alkyl halides are acting as substrates since they have a good leaving group. Next term that we used was a nucleophile. A nucleophile is a species which is rich in electrons. That is, it is a Lewis base responsible for using its pair of electrons to displace an atom or group from a molecule. Nucleophile may be neutral, that is a water molecule, and this water molecule acts as a nucleophile through lone pair of electrons on oxygen. Or it may be negatively charged like an hydroxyl ion, where hydroxyl ion acts as a nucleophile through the negative charge on oxygen. What is a leaving group? It is a Lewis base which is displaced by a nucleophile. That is, it is an atom or group of atoms that is displaced as a stable species, taking with it the bonding pair of electrons. In alkyl halides, the leaving group is an anion, whereas in alcohols, it is a neutral molecule, that is water molecule. And these reactions of alcohols we have studied in detail while we were discussing the preparation of alkyl halides from alcohols, in which we found that the OH group was first protonated to convert it into a water molecule, which was then eliminated as a leaving group. In those reactions, we had converted OH group, which is a bad leaving group, into water molecule, which is a good leaving group. So the better leaving group, as we've demonstrated, is more likely to depart easily. In alkyl halides, since the halide ion is a conjugate base of a strong proton acid, that is halogen acid, and leaves as a stable anion, it is a good leaving group and thus can be easily replaced by a nucleophile. The nucleophilic substitution reactions can be classified into two types, depending on the nature of the substrate and to some extent also on the basis of the reagent and the reaction conditions. The two types of nucleophilic substitution reactions can be SN2 reaction, which is an abbreviation for substitution, nucleophilic, bimolecular, or they may be SN1 reactions, which are substitution nucleophilic unimolecular. In today's lecture, we shall be discussing bimolecular nucleophilic substitution, that is SN2 reactions in detail. So what does substitution nucleophilic bimolecular mean? Substitution means that we are bringing about substitution, that is, we are replacing a halide ion from an alkyl halide. Nucleophilic means that this reaction is brought about by a reaction of a nucleophile with an alkyl halide. Bimolecular indicates that in rate determining step, two species, that is the alkyl halide and the nucleophile, will be taking part in the reaction. Eugen in Gold in 1937 proposed a mechanism for SN2 reactions based on their experimental data. They said it is a single step process where both the alkyl halide and the nucleophile are involved at the transition state of the rate determining step. This you can see on your slides. That is, what I have shown here is a transition state, and what we find that in transition state, nucleophile is making a bond with the back lobe of the carbon at sp3 hybridized carbon, and at the same time the bond is being cleaved between the carbon and the halogen atom. That means at the transition state, both the species, that is nucleophile and the alkyl halide, are involved. That is the rate determining step. It is a concerted reaction. Now, what do we mean by saying it is a concerted reaction? That means the reaction takes place in a single step in which bond formation between the nucleophile and the carbon atom, as well as the cleavage of the bond between carbon and the leaving group, takes place simultaneously. Here simultaneously is very important, which indicates that it is in fact the nucleophile which pushes off the leaving group from its point of attachment to carbon. This is because carbon can have 8 electrons in the outermost shell. So as soon as the nucleophile makes the bond with the carbon, it is must that at the same time that the halogen as an halide ion should be eliminated. So here I have shown the general reaction in which we are showing that the non-bonding pair of electrons from the nucleophile are attacking the electrophilic carbon. Please remember, whenever we have to show the flow of electrons, it is always from the nucleophile to the electrophile and not vice versa. And then a bond breaks between carbon and the halogen atom, resulting in the formation of the product and an halide anion, which is a leaving group. This reaction I have further illustrated by taking an example of reaction of a strong nucleophile, that is hydroxyl anion with methyl iodide. So what we find in this reaction is that the hydroxyl anion, which is a strong nucleophile, attacks the carbon, which is electrophilic in nature, from the opposite side to the bond, which is to be cleaved. And a transition state is obtained in which there is partial bond formation between the carbon and the nucleophile, as well as carbon and the halogen atom. And the nucleophile pushes the halide anion, that is iodide, out, resulting in the formation of the product. So if we summarize this, we can say hydroxide ion is a strong nucleophile and it attacks the electrophilic carbon from the backside, donating a pair of electrons to form a new bond. Now the question arises, why does the nucleophile attack only from the backside? A simple explanation for this query is that a leaving group blocks the approach of nucleophile from the front side of the molecule. Hence, in SN2 reactions, the nucleophile always attacks from the backside of the molecule. As I've already said, that carbon can accommodate only 8 electrons in its valency shell. The carbon-iodine bond begins to break as the carbon-oxygen bond begins to form. That means the cleavage of the bond between the carbon and the iodine molecule, the iodine, that is the which is eliminated off as iodide anion, and the bond formation between the carbon and the oxygen atom takes place simultaneously. That is, this is a concerted reaction. Iodide ion leaves with the pair of electrons that were once bonded to the carbon atom. This is hence a one-step reaction, and this one-step mechanism is supported by the kinetic data of the reaction. We can change the concentration of the reactants and observe the effects on the reaction rate. So the rate is found to double when the concentration of either reactants is doubled, and it becomes 4 times if the concentration of both the reactants is doubled. Therefore, the reaction is first order in each of the reactants and second order overall. The rate equation can be represented as rate is equal to Kr into the concentration of the substrate as well as the concentration of the nucleophile. Hence, we can explain that when we increase the concentration of the substrate or the nucleophile, the chances of effective collisions will increase, which will result into greater reaction rate. So when we double the concentration of the product, the rate of the reaction is found to be double. Now we shall discuss the stereochemistry of SN2 reactions. If we start with an optically active compound, the reaction is accompanied by inversion in configuration. Why does this take place? As you already know, the nucleophile attacks the back lobe of sp3 hybridized orbital. That is, it attacks the substrate from the side opposite from which the leaving group is departing, or in other words, we can say at the angle of 180 degrees. This backside displacement results in the inversion of configuration. By a simple analogy, I can explain that is, if we take of an example of our real life experience, then what we find that on a windy day, our umbrella turns inside out because of the strong wind. This is what I've shown on your screens, that since the nucleophile is attacking from the opposite side of the carbon, from where the bond is being cleaved between carbon and the bromide ion, there is inversion in configuration at the carbon where the substitution is taking place. In other words, we can say backside attack brings stereochemical inversion of the tetrahedral arrangement of bonds to the carbon at which substitution occurs. That is, it turns the tetrahedron of the carbon atom inside out like an umbrella on a windy day. This is known as Walden inversion. So for this, let us discuss an example of hydrolysis of optically active 2-bromooctane in presence of hydroxyl ion, which is a strong nucleophile. It gives 2-octanol having configuration opposite to that of starting alkyl halide. So as you can see on your screens, the strong nucleophile, which is an hydroxyl anion, attacks the electrophilic carbon at 180 degrees to the bond which is being cleaved between carbon and the bromide anion. When it forms a bond, it results in a transition state where a partial bond is formed between carbon and the hydroxyl group, and the bond cleavage starts taking place between carbon and a bromine atom, resulting in a transition state in which carbon is fully bonded to 3 groups and it is partially bonded to a hydroxyl group which is acting as a nucleophile and to a bromine atom which will act as a nucleophile. And this bromine atom is eliminated as bromide anion, resulting in the formation of 2-octanol. Now if we compare the stereochemistry of the two compounds, that is 2-bromooctane and 2-octanol, what we find that the configuration at the chiral carbons is different. That is, in the substrate, the molecule has R configuration, whereas in the product, the molecule has S configuration. So, reaction is accompanied by inversion in configuration. And here we get S2-octanol in 100% purity. That means the reaction is stereoselective in nature. I have tried to explain all the changes that we've observed in an SN2 reaction with the help of a potential energy diagram. So if you look into this diagram, what the 3 things that we have to keep in mind that I've tried to illustrate here, that first, the nucleophile attacks the substrate, which in this case is 2-bromooctane from the backside. And in this case, the carbon of the substrate is sp3 hybridized. If we look into the transition state, then what we find is that the bond between the carbon and the bromine starts extending and it is weak in nature. Since the bond formation as well as bond cleavage is taking place in transition state, both the bonds, that is the bond between the hydroxyl group and the carbon and the bromine are partially formed and are weak in nature. So what we find here is that the carbon in the transition state is sp2 hybridized, fully bonded to 3 groups and partially bonded to 2 groups, that is the nucleophile, the hydroxyl group, and the leaving group, which is the bromine atom, which will leave as a bromide anion. Hence, in this case, the carbon is penta-coordinate and is sp2 hybridized. As soon as we pass the transition state, the halide anion is eliminated and we get 2-octanol. And when we get 2-octanol, here again the carbon resumes its sp3 hybridization. Now, if we look into the stereochemistry of the reaction, then what we find that in the substrate and the product, the configuration of the groups is inverted. That is, the reaction is accompanied by inversion in configuration. If we consider the energy of the reactant and the product, then what we find that the reactant, it is at a slightly higher energy than the product. That means this reaction is exothermic in nature and is feasible. Whereas if we look at the highest energy level, then that is occupied by the transition state, because the transition state is highly unstable and it is, in this case, carbon is pentavalent. What you have to remember that in SN2 reaction we get our transition state which is highly unstable and exists only for a moment. It is not an intermediate, therefore transition state is highly unstable. Immediately an halide anion is removed from here, resulting in the formation of the product. So the 3 salient features that you have to remember about SN2 reactions are, that is, the attack of the nucleophile will take from the backside of the reaction of the carbon from where the halide anion is being eliminated. In the rate determining step, 2 species, that is the reactant and the nucleophile, are taking place, and the reaction is highly stereospecific since it is inverted by inversion in configuration, and we get the product in 100% yield. Let us take another example of Walden inversion. In this I have shown the reaction of cis-1-chloro 3-methyl-cyclopentane with a hydroxyl group which is a strong nucleophile. Here again we can see that the hydroxyl group attacks the carbon from the opposite side from where the bond will be cleaved between carbon and the chlorine atom, resulting in the formation of trans 3-methyl-cyclopentanol and the chloride anion, which is the good leaving group. Now what we can presume that the transition state for this reaction is shown as I have represented in the slide. That is, in transition state there is partial bond formation between the carbon and the hydroxyl group, which is a nucleophile, and it takes place from the lower side of the ring, whereas leaving group along with the bonding pair of electrons departs from the top side, resulting in the change in configuration. That is, from cis isomer we are getting a trans isomer. In my next lecture, I shall be discussing the effect of various factors which will affect the nucleophilic substitution reactions, that is, the nature of the substrate, nature of the nucleophile, nature of the leaving group, and the nature of the solvents in which these reactions will be brought about. Till now, I have not mentioned solvent anywhere in these reactions. We shall be discussing these factors which affect the bimolecular nucleophilic substitution reactions in detail in my next lecture. Thank you.